Hello, so we are looking into power system analysis and we're doing the per unit analysis. Per unit is a part of the study of non-dimensionalities, and what we're trying to do is to give characteristic units with dimensionless variables. And this is a simplifying technique, although it might be terrifying and confusing in the beginning, but what we're doing is actually to simplify the circuits so that we can apply basic electric circuit analysis to solve our problems. So let's take a look at a very simple voltage drop problem. Here we have the V1 where the voltage is generated, and then we have some current and some impedances that are causing a voltage drops, and then we want to find what is the voltage at point A. So what we will then do is to first set up VA, which is equal to the generated voltage at Vn minus the current times the impedance minus the current times the impedance at impedance 2, and then we can put this together here with the sum of the impedances and find the voltage at VA. So that is a very simple task to solve, but as our circuit elements increase, we will see that it's much more complicated. And let's put one circuit element into this problem, and that's a transformer like this, and the transformer will transform from one voltage level to another voltage level, which means that it has a turns ratio between the high voltage side and the low voltage side, or you can also refer to it as primary and secondary, as you like it. So let's say that this side is N1, then this is N2, and it means that there is one voltage level here, which we will denote as V1T, and then at the opposite side there's another voltage level which we will denote V2T. So in order then to look into VIT, or V1T as we have called it here, we need also to differentiate amongst the currents. So it's not no longer the same current here, because as we're changing the voltage, also the currents are going to change, but the power is going to stay the same, so the relation is equal among them. So if we look at that V1T, that is going to be here V1T is equal to V1 minus I1 times Z1. So that's the very first step. And then we need to take into account the relation between V1T and V2T in order to find V2T. So that means that we know that V1T, here's V1T over V2T is nothing but the relation between N1 and N2. So you can see it there, N1 to N2, right? And then the task is to single out this V2T. So what we can do then is to multiply the whole story with V2T times N2 over N1. So that means that we are left with here V2T is equal to V1T N2 over N1. And then we are looking at VA again. So it means that we have here that VA is equal to V2T, and we have found that relation here. So that is going to be V2T minus I2 times Z2. So that means that we have moved over to the V2T side. And then we cannot use this I2 because we don't know how is the relation yet between I1 and I2. So we have to do that relation as well. And that's going to be I2 over I1. So just take a note of that, that here is the opposite relation, although it's still N1 over N2. But as the voltage is changing, the current is changing, but in the opposite way. So that means that we need to, at the same time, have both of these turns ratio in mind as we're solving the problem. And that's what's going to complicate the whole matter. So, although this is a bit easier, because here I just need to multiply by I1, so it means that I2 is equal to I1 times N1 over N2. And then we're back to VA, so we have here VA is equal to V2T minus I2 times Z2, and that is then going to be VA is equal to V2T minus this relation here, which is then I2, which is going to be I1 times N1 over N2 times Z2. And then the last thing we are going to do is then we're going to put in this relation for V2T. So that means that we have here at the bottom stage, VA is equal to V1 minus I1 times Z1 N2 over N1, since that's coming from this point. And then we have minus I1 of N1 over N2 times Z2. So when you're solving a problem like this without any conversion into the non-dimensionality, and you're sticking with the turns ratio, you always need to consider what is the turns ratio of this side and what is the turns ratio of the other side. And that's going to be very, very complicated when you make big networks. So that's why we're using the per unit analysis to solve big electrical networks.